roughly 168,000 light-years from Earth, something is happening that no model predicted. A neutron star, the collapsed core of what used to be a massive star, is emitting a signal in the infrared. That by itself is not unusual. What's unusual is the pattern. The signal is structured. The ionized gas surrounding the star is not randomly distributed. It forms a concentration pointing back toward the center, toward the dead star itself. James Webb Space Telescope captured this in late 2024 while surveying the remnant of Supernova 1987A. The star that died there left behind a neutron star roughly 20 kilometers across, packed with more mass than our Sun. For 37 years, we knew it was there, but we had never seen it directly. The debris cloud was too thick. Webb changed that. And what it found was not a simple cooling object sitting quietly in the dark. Supernova 1987A is the closest supernova observed since Kepler's star in 1604. When it detonated, it was bright enough to see with the naked eye from the southern hemisphere. The star that exploded, a blue supergiant cataloged as Sandelique -69 degrees 202, had been burning for roughly 12 million years before the core ran out of fuel and collapsed in less than a second. The physics of that collapse was well understood. A massive enough core compresses under gravity past the density of an atomic nucleus, bounces, and sends a shockwave outward. The outer layers of the star get blasted into space. What remains at the center should be a neutron star, roughly 1.4 solar masses squeezed into a sphere about the size of a city, spinning fast, radiating hard. But for 37 years, direct observation was impossible. The expanding shell of gas and dust the explosion threw outward was opaque to most wavelengths. Hubble could image the beautiful ring structure of the outer debris, but the center stayed hidden. Chandra, NASA's X-ray observatory, picked up emission from the ring as the shockwave slammed into surrounding material, but the neutron star itself remained behind the veil. Some astronomers began to quietly wonder, what if the neutron star had collapsed further, straight into a black hole, skipping the stable neutron star phase entirely? A black hole would explain the silence. There would be no pulsar, no persistent thermal emission, nothing easy to detect. The question was genuine. Webb was pointed at 1987A to get an answer. The instrument that resolved the question was NIRCam, Webb's near-infrared camera. It detected argon and sulfur ions concentrated at the center of the remnant. These are atoms that have been stripped of electrons, and that stripping requires a source of intense ionizing radiation nearby. The source is the neutron star. At a surface temperature estimated around 5 million Kelvin, roughly 1,000 times hotter than the surface of the Sun, the neutron star has been steadily radiating since the moment it formed. Webb's sensitivity in the mid-infrared finally cut through 37 years of accumulated dust and resolved the emission. The neutron star was there. The physics was right. But the ionization pattern was not what researchers expected from a simple cooling neutron star. A standard model predicts a fairly smooth, spherically symmetric distribution of ionized material close to the source. What Webb found was structured, a concentration of argon ions that implies either directional energy output, a pulsar wind, or something actively injecting energy into the surrounding gas. The mass of the neutron star is estimated at 1.4 solar masses compressed into a sphere 20 kilometers in diameter. Surface gravity is approximately 200 billion times Earth's. A single teaspoon of its material would weigh around 10 million metric tons. Escape velocity at the surface is roughly half the speed of light. And right now, this object, dead by stellar standards, but still intensely active by any other, is doing something no current model fully explains. One leading interpretation is a pulsar. If the neutron star is rotating rapidly, even a few times per second, it generates a powerful magnetic field that accelerates charged particles outward in jets. Those jets ionize surrounding gas in a directional pattern. Webb doesn't directly detect the rotation timing signature, but the ionization structure is consistent with pulsar wind nebula formation at a very early stage. Radio telescopes have been searching for the pulsar signal, but the dust cloud appears to be absorbing it. For any serious thinking about long-term human presence in space, the physics here matters more than it might seem on first read. Neutron stars are not just exotic end products. They are the delivery mechanism for heavy elements. The iron in your blood, the calcium in your bones, the nickel at Earth's core, these were forged in stellar interiors and dispersed by supernova explosions like the one that made 1987A. Gold and uranium require something even more violent: neutron star mergers, where two of these objects spiral together and collide. Every heavy element above iron on the periodic table has a neutron star somewhere in its origin story. The question for any colonized system is not whether you'll encounter the downstream effects of stellar death. You already live in them. The question is what happens to a settlement if a nearby massive star goes supernova during the colonization window. At 100 light-years, a supernova delivers enough gamma radiation to strip a significant fraction of a planet's ozone layer. At 25 light-years, the radiation environment becomes potentially lethal on geological timescales. No known star within 25 light-years is a near-term supernova candidate. But the galaxy is large, and the timescales of multi-generational colonization overlap with the timescales on which stellar evolution models carry meaningful uncertainty. Knowing what happens inside a post-supernova remnant in real time, what the young neutron star is actually doing, how it energizes its environment, how the debris cloud evolves, is directly relevant to radiation hazard modeling for any settlement within a few hundred light-years of an active stellar population. Webb's data on 1987A is the most detailed close-range observation of a young neutron star we have ever obtained. That baseline matters. The observations leave several things unresolved, and researchers are actively debating all of them. First, pulsar or not. The ionization structure is consistent with a pulsar wind, but it is not conclusive. If the neutron star is spinning rapidly, a pulsar detection in radio would clinch it. So far, the dust cloud appears to be blocking the signal. Longer radio observations with upgraded facilities may eventually cut through. Second, is the energy output steady or intermittent? A pulsar wind is more or less continuous. But some models of young neutron star evolution predict episodic energy injection, bursts driven by cooling instabilities in the crust or by magnetic field rearrangement. If the ionization pattern is driven by something intermittent, it has implications for how quickly the remnant evolves. Third, there may be a disk. Some of the infrared excess near the center is consistent with a debris disk, material that fell back toward the neutron star after the explosion and settled into orbit. If confirmed, this would be the first direct observation of a fallback disk around a neutron star in its birth environment. Fallback disks affect how quickly neutron stars accrete material, how they spin down, and whether they can eventually power a different class of emission. The data is suggestive, not conclusive. Webb observations of 1987A are ongoing. Each new dataset refines the picture. For 37 years, we trusted the physics. A star collapsed, a neutrino burst hit Earth 168,000 years after the fact, and we inferred that a neutron star had to exist somewhere inside that expanding cloud of debris. We built models. We argued about whether it had become a black hole. We waited for an instrument sensitive enough to actually look. Webb looked. The neutron star was there, and it was not sitting quietly. It was ionizing its environment in a pattern that demands explanation, and the explanations being put forward require us to update our models of how young neutron stars behave in the first decades after formation. That's what makes this more than a data point. Supernova 1987A is close enough and old enough and now visible enough that it functions as a real-time laboratory for stellar death. We can watch the remnant evolve. We can test ideas against actual observations instead of inferences. The dead star isn't done, and neither are we.